Okay. And now
Yeah, I think the room was not included in the email, but I think everyone knows. That is the actual.
I put it on the webpage.
On the webpage, yeah.
Perfect.
So if anybody has any questions, ocultar esto. Y this is you. And for you to know, then we put this here. And then, I have this. I broke it.
Oh, perfect.
This is mine. For you. I decided to buy one of these. Espera.
That's it.
Oh, no. Ya funciona.
Yeah.
Sí.
Yeah. So this is for it's simple.
Exactly, because this always counterintuitive for me. What's the brown one? I always
Exactly
go
what I was doing. I was
back.
thinking I was not working because of that. Yeah.
Okay.
And it has also
That's
laser.
fun.
So.
Exactly, because
My
it's
first
clear
time.
if you don't switch, but when you start switching, then it's not
Yes.
fun.
I hate the
That's
pointers
fun.
because even though if I'm not completely stressed, it happens to me that with the pointer, just natural movement of my hand sounds like, squeaky.
Yes.
And then I become completely stressed because it's so, I'm nervous, I'm nervous, and then it starts to do like.
People can see it.
So for you to know, to see what the people is seeing, let me
check also on YouTube. So.
Then you can see us. People that is in YouTube, that subscribe to the channel, they receive a notification.
That we started.
Yes, I received the notification. I'm subscribed.
You have to be subscribed.
Yeah.
He's my yes. She was asking whether he was
Perfect.
for you to know the okay, so
I can hear.
because it's too much. So what you see so you see the whole people can see
It's a bit. I think you should do it.
I have to do what?
Close this.
And then I well, in the
No,
computer,
you can.
not here, but well, in the computer.
You can zoom to
you can zoom. So you have the whole. If you want to write anything, you have the whole thing. If you want to send me your slides for those things that are not visible because you cannot move this.
Okay, yes.
So there may be some things on the.
So you will
That's
share
right,
them.
corner. So we can upload it to the web page.
Definitely, yes.
Good. Okay. So we will see. Let's wait a couple some minutes because people is always. I mean, we never start that on the upload. It's not our thing. At some point we start.
I'm learning these.
Yeah, to Spanish, and it's not my taste, I must say, but.
It's very common.
No, in Italy also, I'm Italian, and there is the Paul. I think we say something
We say the same.
there is a name.
The what?
For the delay in the beginning at university. The class doesn't usually start at the sharp time.
Yeah, the past 5 or
Like
something like that.
5 minutos político.
I
Something
say
like
the same. It's like
Same thing,
for
okay.
the sake of courtesy or something like this.
For the sake of.
5 minutos de cortesía. No?
Courtesy, you want to say.
I don't know if there's translation in English.
That there is no translation.
There is no.
The courtesy is to be on the clock. That would be interesting.
Yes. Yes.
There will be a contemplation. You must speak German.
No,
I guess,
not at
no?
all. Not at all.
So, but there will be a very long explaining that the typical thing that the Spanish do that we don't do. Explain the whole.
Yes.
One word.
One word, of course. Come on.
But
Why to
actually,
speak
in
in two?
Germany, there is I think the classes, they have a time, but they actually start 10 minutes later. But everybody knows. Like you would read the schedule and it's like 9, but actually it's 9:10.
Yeah, to allow the people change from classroom to classroom, of course. Like we are supposed to end at -10.
So
And then the next classroom starts on the, o'clock. But the thing is, but then always happens the same. You never end at -10.
And then there's like
And then the next professor is very angry with you. And then the next professor also ends later. And then the next one is you come to it starts on the clock at 9 in the morning, and then it's at whatever at 7 p.m. You know if Angel is coming or
if Angel is
or
here.
parleremo, ci sarà un'altra occasione.
good. So we have the Italian speaker.
You can speak Italian.
Yo hablo
Don't worry about
español, pero como no es muy profesional, preferisco no hablarlo. Es que depende de situaciones que estoy bastante como tranquila hablándolo y ahí es que depende, creo, desde el topic, si conozco todas las palabras o no, entonces por trabajo prefiero inglés. Pero entiendo. Entonces, si dices cosas malas,
Me voy a entender. As I did so. Like in the past, I remember, I was a little kid going to UK and remember with other little kids, and at some point somebody was saying, looking for another friend. Where is that friend? She sit there. Sit where? Yeah, next to the fat guy, but in Spanish. Al lado del gordo. And then el gordo, I understand. Oops. So typical. Yes. Let me, what I was going to do? I was going to put here the YouTube channel and see if anybody was connected. And also to have it here. Yeah. To finish 35, we can start. So sorry for there are 2 people already watching, so we can start. Yeah. So let me just introduce you. So welcome everybody. Today we have Claudia Fevola from CUNEF. We are very pleased that she was able to come here at different time than the usual, but she's going to talk us about KP Solitons and tropical cores when tropical cores meet Grassmannians.
Thanks a lot. Thanks for the invitation. I'm very new to Madrid personally and professionally, so it's very nice to meet other math people outside CUNEF and especially neighbors. So very happy to be here. Thanks, Marina, for the invitation. So this is a talk, so I'll get to explain all the words in the title, and this is a joint work that appeared at the end of last year, together with Simonetta, Türkü, and Yelena. And so I have to say, Simonetta Abenda, she's the math physicist in the team, while Türkü Özülüm Çelik and Yelena Mandelshtam were more on the combinatorics and algebraic geometry on the story, and we realized that it would be a very good idea to actually join together to understand this connection. So the main character of the talk is the KP equation. So this is maybe very well known to especially integrable systems and math physicists. So this is a partial differential equation that depends on 3 variables, x, y, and t. And so x and y play the role of space variable, and time is t is the time variable. And this is a tiny, so it's a small piece in a much larger story. So this is the second non-trivial equation in the KP hierarchy. So in this integrable system of infinite equation. And so the solution to the KP equation is a function of these three variables, and we're interested in what are called finite gap solutions. So these are solutions that can be written in this way, and so an equivalent condition is that so for P to satisfy the KP equation is that this function called the tau function of the KP equation satisfies this is called the Hirota bilinear identity. So now in the rest of the talk, we're mostly gonna talk about the tau function of x, y, t. And so here I stole this picture from the paper by Agostini, Selic, and Surfeld about, so this is one representation of a solution to the KP equation of this type. And so one of the reasons why this talk fits the scopes of the seminar very well is that KP solutions are connected to algebraic geometry via algebraic curves and Grassmannian. So I'll try to tell you in the first part of the talk an overview of these topics. And so as I said, so this is the reason why we're interested in these finite gap solutions, because these are the ones that can be built from algebraic curves. And so in the complex realm, on this side, we have smooth complex algebraic curves, or Riemann surfaces, if you prefer, together with a choice of a divisor on that. And then actually all solutions to the KP hierarchy are parameterized by points in the Sato-Grassmannian. So this is an infinite version of the usual Grassmannians, of finite Grassmannians. And I'll tell you slowly a bit more. So in the first connection, in this first connection, the connection was initially established by Krichever, who gave basically an explicit recipe for building a solution from an algebraic curve. So the main ingredient for doing that is the so-called Riemann theta function. So this is a function of a complex vector z, where here G, I haven't mentioned it, G is the genus of the curve. And so the Riemann theta function is not necessarily associated to a curve, but when, so the reason why I am choosing G is because we're gonna take Riemann functions associated to the curve, and in this case, G will be the G. Then Z is one parameter, the other is B, which is a complex symmetric matrix with positive definite imaginary part. So this is called the Seeger-Peralta space, to people that have heard about it. And the Riemann theta function is an infinite sum over the integer lattice of exponentials. In the argument of the exponential, so there is a quadratic form that you get by multiplying your integer vector with the matrix B, and this linear form given by C transpose Z. And this condition is what ensures absolute convergence of these infinite series. And in the case in which we associate the Riemann theta function to an algebraic curve, this matrix B is what is called the Riemann matrix of the curve. So it's a matrix that can be built by periods of the curve. And so what this is so what Krichever did is to associate a solution to the KP equation in this way. So you have to make choice of a point, a distinguished point on the curve, a local parameter, and then solutions to the KP equation will be parameterized by the different choices of divisors of degree G on the curve. And basically, in Krichever recipe, you get how to build the U, V, W, and D. So this is this three vectors will depend mainly on the curve, and D will be the part coming from the device. And the other side of the story, so the Grassmannian story, basically points in the Grassmannians are represented by infinite dimensional matrices. So here I have infinitely many columns in this direction and rows are infinite many. But because of the shape of the matrices, so here at some point I just have one on the diagonal, so I can kind of make sense of minors. There's a way, there's combinatorial tools. So here there's a sum which will be indexed by a partition, and this entry here, this will be a number that comes from like these minors I can get from the matrix. And these are Schur polynomials. And basically, the idea, so the Sato's work is about building this tau function in terms of Schur polynomials, and this will give all possible solutions to the KP hierarchy. The story I care mostly about is the one that connects to tropical geometry, and the reason, so the way from one way of moving from here to here is via degeneration. And so on the KP side, the motivation is that there is a family of solutions which are called solitons that I will slowly tell about, that will play the role over here of the solutions. In the curves realm, under the generations, I allow singularities of the curve. And so this will be singularities which are at most nodes. That's the worst singularities that I am going to allow in the rest of the talk. And on this side, so as I mentioned, the Grassmannians in particular contain the finite Grassmannian, so usual linear subspaces inside an dimensional vectors. So what are these objects? So a KP soliton, at least from like algebraic geometry point of view, is mainly something of this type. So it's a finite sum of exponentials that I define by first fixing n parameters, k1 to kn, that are real parameters, and say now, for now, these delta I are just complex parameters. And then here I have a finite sum. I'll tell you slowly, I'll tell you in a second more why I'm using this notation, of over subsets of the integers from 1 to n. These are parameters. These ki are these van der Monde determinant of matrices built from these kapis. And then the ei, as I mentioned, are finite exponentials. So this set capital I is a finite set, and then I get the product of these exponentials that depend on my kappas. And so the reason for this notation is mainly, so again, due to Sato, that these KP soliton solutions are parameterized by points in finite Grassmannians. So basically, n will be the n in the Grassmannian, and then these delta I are basically Brugger coordinates. So if I can find a matrix I for which these parameters are actually Brugger coordinates, then my solution is a KP solution, and the vice versa also. So example, just to get more familiar with the notation. So this is my matrix A. In this case, I have 4 parameters. This is the matrix of kappas from which I get the these van der Monde determinants here. And these are so the products of my capital EI at the end will look like something like this. Okay. So as I mentioned, so this is where I, together with collaborators, came in trying to connect this side of solitons and solutions arising from singular curves. So The idea here is to define the curve over a non-empty medium space. So you can think of it as a finite extension of the rational numbers together with the parameters or the fields of Fusee series. And the idea is to plug in this parameter epsilon in our smooth curve and then see what happens for epsilon equals to 0. And one nice thing about the degeneration is that up to, of course, like missing maybe some information, but there's a lot of things that you can read by looking at the combinatorial data. And this is given by the dual graph. So this is a graph. It's called that way because every node will represent a component of my curve in the degeneration, and then I have edges anytime two components intersect. And so self nodes, so loops here correspond to self intersections. So they are nodes on the curve. And so this is, for instance, this should be the dual graph of this component. So for instance, the purple thing has a puncture, and then green and purple, they intersect and so on. Okay. And I allow, so stable degeneration, which means on the graph that every vertex is not true in this example, but in general, I want all my vertices to be trivalent. And as I said, word singularities are not, so I can have loops. And also, so the one more thing is that every the degeneration is to rational components. So every curve eventually is a copy of a P1. And so together with tracing this degeneration here, we want to trace the degeneration on the Riemann theta function. So I want to plug in my parameter in epsilon and see what happens to the Riemann theta function. So here Z will depend on epsilon, B will depend on epsilon. And now the spoiler, we will see this degeneration better soon. But eventually, the Riemann theta function will be supported on a finite set in ZG. So this should be remember, like eventually we're going to have a finite sum of exponential, which is what we had for solitons. So this is a bit the intuition. And there's one more piece that you can add to the story, which is if it were about reality of solutions. And I think especially math physicists do so, one can offer reality and regularity of the solution. And here I just want to mention that there are counterparts in the three pictures. So on the algebraic curves case, there will be M curves. So these are the capital M stands for maximum, which means that they are so the real curves with the maximal number of ovals that you can have. So you can prove that there is an upper bound on the number of ovals of the real part of curve. This is genus plus 1. And M curves are precisely those that achieve this G plus 1. So this is, for instance, a genus 3 curve. And there's a condition on the divisor for having real and regular curves, which is that the divisor, every point has to lie in one of the ovals. And there's also a counterpart here. This has been explored very little, so far I'm aware just of one paper that gives the definition, but I think here there's way more work to be done, where you just ask for positivity of these Kluger coordinates in the Salzburg medium. And then you can combine real and tropical as well. So you can talk about real regular solitons. This will correspond in the Grassmannian picture to having points in the non-negative, totally non-negative Grassmannian. So just Grassmannians with whose Kluger coordinates are positive. This was studied in depth by Kodama and Williams, where in fact they proved that the real and regular solitons just correspond to these positive to performing it. And so we explored also like the combinatorics of soliton graphs that you can build and so on. And this is something on which Simonetta also has worked on together with Piotr Grinevich. And basically, the idea is that you want some non-crossing condition in the normalization together with this condition on the divisor. And this is also something on which we plan to work more in the future. Okay, so this was the full panoramic view of the field, and at least an attempt, let's say. And there's of course, I mentioned some people, there's of course many more works. So from like the Japanese school, for example, these are some sort of recent papers by Ichikawa and Nakashiki. And also this is a very recent also like survey on integrable system and algebraic geometry. And here I just want to also mention that there's a important connection, so an important motivation for studying this KP equation and algebraic curves in connection to the Schottky problem. So there's maybe, yeah, for people that might have heard about it, so the only general solution, so for every, which is known for every genus on the Schottky problem, relies on this KP connection. And then people is like looking for purely algebraic geometry solutions to the problem. Recently, I also learned about connection to, I didn't learn about it, I read about connections to Irvis numbers. So it's very broad. Okay, so now I get to the connections to this more recent work. So in the rest of the talk, I will explain more in detail the connection to how to perform this limit on the Riemann theta function. And so polytopes will appear in this picture, so Voronoi and Delaunay polytopes. And then, so in this recent paper, we focused on one family of curves, which is the one represented by banana graphs, which is, okay, I'll say more soon. And so I think people in tropical geometry will not say banana, would not call these banana graphs, but or like dipole. I think people in theoretical physics call these banana graphs, but I was easily convinced by my collaborators to stick to banana, so that this talk could be about waterways, tropical geometry, and bananas. So. And so the main topics that will come out here are, as I said, these Voronoi and Delaunay polytopes. We'll focus on KP solitons, and there will be a smaller part if there's time to strongly connected orientations of the graph. Okay, so this is the first part of what we need for to perform this degeneration. So I need a counterpart of this Riemann matrix of a smooth algebraic curve. And so there's something called the tropical Riemann matrix. I think in the literature, sometimes people also call these Laplacian or second Laplacians, dual Laplacians. There are other terms as well. And it's defined in the following way. So I take a basis of first homology of the graph, gamma 1 to gamma g, so g is the genus of the graph and of the curve. And I define a matrix B, which is just the one that keeps an integer basis representing these cycles. I haven't mentioned that, so these graphs, they come with orientation and also edge length that represent the different degenerations that you have morally. And then you build the matrix Q, which is given by B times this diagonal matrix times B transpose. So here's one example. This is, for instance, one hyperelliptic curve in genus 2. And then, as I said, the idea is that I plug in a parameter epsilon inside my curve. And so this is given by 2 copies of P1, given by the vertices that meet with 3 branch points that will be given by the 3 vertices. In my matrix B, I take, so for instance, this is one basis, A1 minus E2 will give 1 minus 1, 0. E2 minus E3 will contribute 0, 1 minus 1. Here the edge lengths are given by choose. And then eventually I get, in fact, a symmetric matrix, this time with integer entries. So this is one counterpart of this degeneration. And now, as I said, I want to plug in this dependency on epsilon in my matrix, in my entries of the theta function. And so to do that, I first fix a value, a vector A in Rg, and then my vector Z get shift by something that depends on epsilon now, and my matrix Q. And then the matrix Q becomes the following. So Q is my tropical Riemann matrix, and R of epsilon is, you can think of it as a symmetric matrix whose entries are analytic functions depending on epsilon that you expect to converge when epsilon goes to 0. And so we plug in these terms in the theta function, and here I'm just splitting the terms that depends on epsilon with the part that does not depend on epsilon. And now the question for this infinite sum to converge in the limit I have for which condition this exponential converges, which is you just want the argument to be smaller or equal than 0. Now with some manipulation, this condition smaller or equal than 0 can be rewritten in this way. And now this is sort of a very geometric, nice condition on the lattice. So now we're asking for all points in Rg, which are closer to the origin in the metric induced by Q than to any other lattice point in Rg. And this is something called the Voronoi cell. So this is the example in the Euclidean metric. This would be just this blue cell here. This is 1 half, 1 half. So these are the points which are closer to the origin than to any other lattice point. Occurs the boundary is where the equality is achieved. And so what happens now is that in the limit for epsilon that goes to 0, these things will either go to 0 or 1. And in particular, it will go to 0 precisely when the equality is achieved. And so this leaves me with what are the points that will actually survive are the integer points for which the equality holds. Okay, so these are the points for which here I get e to the 0, so I get 1, otherwise they just disappear. And so we've just proven the following. So if we fix our vertex A to be a vertex of the Voronoi cell, then in the limit for epsilon that goes to 0, my infinite sum of exponential becomes a finite sum of exponential supported on the vertices of this Delaunay set D that depends indeed on A and Q. And here the notation, so this is the AQ, and then this AC is the part that we remember of the R part. So this is basically this one. This is the exponential of C transpose Z, and the AC comes from this part over here. So, for instance, how does this limiting Riemann theta function looks like? This is another, the other possibility that you can have in genus 2. And this is one case in which the metric is indeed the Euclidean metric. And so the support of my theta function in the limit will be just the square with vertices binary. This is one more sample. So this is the example I started. Yes, this was the same degeneration I showed when we compute the matrix B. We saw that the metric was this one, and so this gives a bit a more interesting Voronov cell.
One question.
Please.
How are you? I mean, these generations are still, each point of the derivation is still a solution for the equation?
No, then no. Okay. That's one of the points of yes.
Okay. But I the final will be
morally you expect that all these solutions that you get from curves, there will be solution to the case. Okay. But you have to prove it.
But after the degeneration, when you end the degeneration.
Yes, exactly.
But not in the process. Who knows?
Yeah, very good question. I've never thought about it.
Nobody knows. Okay.
You mean not at epsilon equals to 0,
exactly,
but somewhere in between?
Yeah.
Yeah, okay. There's something, so you can do, so for instance, now I'm degenerating the curve, I'm taking the worst degeneration, right? So, yeah. But you can do partial degeneration of the curve. So for instance, you say, maybe. Okay, this is best. Say instead of having, so in genus 2, I get to having one component with 2 nodes, you could ask for partial degeneration, so just allow 1 node. So something not rational. You don't get a copy of P1. And I think there are in the KP frame, there are solutions. It will be something mixed in between the solution from the smooth curve and the usual one, and the part which is finite. Yes. Okay. This hasn't been studied so much. So worse degeneration than nodal have been studied. The idea is that from the smooth curve, the theta function is an infinite sum of exponential. Then the curve becomes worse, the theta function becomes nicer somehow, right? Then the worst degeneration, so you can allow casts, for instance, the theta function becomes polynomial. This has also been studied and is also connected to families of KP solutions. I think partial degenerations is a bit more less explored.
Thank you.
No problem. I think maybe in the South Grassmannian, this would be more visible. That should have some pieces corresponding to a finite Grassmannian and some pieces, but this is speculation.
I see.
Okay, so in this other example, the metric is induced by this tropical Riemann matrix, and for instance, and this is the Voronoi cell in this metric. And when I fix, for instance, A4 to be this vertex, then the corresponding Delaunay set is this blue triangle. And now my Riemann theta function is supported on 0, 0, 1, 0, and 1, 1. And this is how it looks like. I'll clarify later why the 2 colors and this choice. And then, so for instance, this is what happens in genus 3. There are 5 possible stable rational degenerations. And these are the corresponding graphs. In fact, so for instance, here I have genus 1 elliptic curve and a line. This will correspond to a vertex with a loop, and then the line intersecting in 3 points. And then the Delaunay set that can appear are not necessarily 1. So, for instance, the thing is that in genus 2 is always 1 type. So just in genus 3, But basically, so one thing I could mention, so this Voronoi and Deloni is actually part of a bigger picture. So they are decomposition of the space and the lattice. So the Voronoi decomposition gives a decomposition just in Voronoi sense, which is always one. And then depending on the vertices, you get different polytopes that tessellate your space. And here, so for instance, we can kind of distinguish, so the Deloni set is just triangles, but we can see that there are two families. So one is pointing downwards, one is pointing upwards. And we try to make sense of this. In genus 3, you can have like two different Deloni polytopes and so on. And we wanted to better, so this is related to compactified Jacobians deeper algebraic geometry problems. And we wanted to understand these pictures in terms of KP and what have you. So banana graphs are graphs of this type. So I always have two vertices and edges connecting them, where n is genus plus 1. And I fix here, so for convenience, one matrix B representing my family of cycles. So I usually take U1 minus C2 and E1 minus N like this. And in this way, the metric becomes this one. And this will be the notation for the Voronoi and the Deloni polytope in what followed. And so let me say one more word here. So the reason why we looked, so the first family, we wanted to initially do this in general for every graph. Then we realized this was richer and harder than what we expected. And so one strategy was to look at families of graphs. So together with Yelena, we previously looked at the case of irreducible rational nodal curves that correspond to these graphs. And so this was a next natural family that you can think of to study in more, so to get something which is sort of homogeneous in the genus and results of it. And so one first thing is that in this case, we're able to say how does the Voronoi polytope look like? So this is the theorem that describes it. And so, okay, let me read this. So given our graph, then we can describe more in general the F vector of the polytope, and we group the vertices in these classes that depend on K. So they're described depending on a value K, and K runs from 1 to G. And so the reason why we group them in this way is that we're basically interested in the combinatorial types of Deloni polytopes that arise. And these, so you say that two vertices of a Voronoi polytope are in the same equivalence class if and only if they differ by a Deloni set. And in general, so in the Deloni subdivision, so in the general framework, they are in relation if you find an integer vector that can shift them. Since here we're interested mainly in this cell center at the origin, this was more convenient. And so this gives also consequently a translation between the corresponding Deloni vertices, so they're the same. And so basically the reason why we group them here in this way is because vertices corresponding to the same K, they will have the same Deloni polytope. And so this was the case here, for example. So here I grouped 1 and 2. And here, so I want to distinguish, so these ones are not the same of the shifting by an integer. You cannot find an integer that translates them. So for example, A2 is equal to A1 minus 0, 1 that shifts the green one to the green one. And so for these banana graphs, we can give the full description of these different polytopes that appear here. And the polytopes that appear will be Haber-Stick. So what are hypersimplices? They are convex hull of sum of indicator vectors where the sum runs over k subset of the integers 1 to n. So this is usually a n-1 dimensional polytope in Rn, because every vertex sum to k. So first examples are delta 1m, delta 2, is the convex hull of the standard basis vector, or delta 2, 4 will be the convex hull of 1, 1, 0, 0, 0, 1, 0, 1, 0, so all vectors including 2, 1. And so as I mentioned, these are the polytopes that appear in this setting. So given a vertex in a class of the Voronoi polytope associated to the banana graph, then the polytope, so this is a linear transformation on my Delaunay set via the matrix T. B is combinatorial equivalent to an hypersimple set. And so one reason to work here is that, so if you remember, this matrix B was number of cycles times number of edges. So by doing B transpose times DAQ, you move in the space of edges. So usually DAQ leaves, like in the examples I showed so far, this leaves in the in RG, where G is the genus, while B transpose times this one belongs to the space of edges. And basically, okay, and then from these coordinates, it's easy to find the shift for which I can say the entries are precisely the vertices of my hypersimplex. And these Voronoi cells are usually also zonotopes. So it means they're, one definition of zonotopes is that they are a projection of a hypercube. And so this is precisely the hypercube where, so the signs over here of each vector of the, so if I take the hypercube with these vertices, the signs will correspond to the signs of my, to the signatures of the vertices of the polytope. And so this idea of working in the space of edges was inspired by these works by Odysseus Shadi. As I mentioned, like this is connected to compactified Jacobian varieties. So a consequence, this was about this transpose. An easy consequence is that these DAQ are hypersimplices. And then one thing is that, so these hypersimplices are usually are matrix-based polytopes of the uniform matroid. So the uniform matroid, this is maybe like for people that have heard about matroids before, is the matroid whose bases are all subset of k elements in 1 to n. And then there's a polytope I can associate to this matroid, and that's precisely the hypersimplex. And so this sort of gives a way of thinking how to associate to my Delaunay polytope also a matroid that I'll say soon what we care about. So okay, I wrote this on the slide. So this is the matroid with basis all the sets with k elements. And then the matroid polytope is the convex hull of the indicator vectors associated to the basis. So you directly get, that's basically the definition of the uniform of the hypersimplex. So in this example, what happens is the following. So I have these two families, and for instance, I take the vertex minus 1/3, 2/3 that correspond to this Delaunay set. Then this is the B transpose DAQ. So now I have 3 coordinates, in fact, number of edges. I can define this shift vector as 0, 0, 1. And then if I apply this, I directly get the coordinates of delta 1, 3. If I do it for this other family, the same process will lead to the hypersimplex delta 2, 3. And these are then the matroid associated to it. So it will be the matroid, here I have just 1, 1, and 2. Here I have 2, 3, 1, 3, 1, 2. And so this is also like correspond to our intuition of like dividing it into these two classes, even if they are the same Delaunay polytope, but you want to distinguish them somehow. And okay, so now I need to connect back to KP. And so the idea, so together with this picture I talked about so far, there are different ways of constructing now from this degenerate curve the KP solution. So on the graph side we're seeing we have banana graphs. On the curves these represent the hyperelliptic curves. So one degeneration possible is this one where I send epsilon to 0 and I get something like this. And the Krischer data was, I mentioned in the very first slide, was a point on my curve. So now this will become a point on a component, and then a divisor of degree G minus of degree G here. And then let me call D0 the divisor I get to restrict to this component I specified by choosing a point. And so, for instance, in previous works by Nakayashiki and Simonetta, there were they constructed this matrix for this curve.
K has to be the genus of that component or not?
G here?
No, K. K.
No. So K, exactly, very good point. K is the number of points that will lie on my component x0.
Okay, but nothing to do with the. Okay, yeah.
Makes sense. So it's actually like a very good point that so also K in my soliton Kn can be has a relation to her. And this is more general than here. Anytime K will be the restriction of so the number of points on the component that contains the distinguished point. And so this is, for instance, the soliton they built from over here. Exactly. So for here, so for this one curve, so in genus 2, I don't have many choices, but still I have two choices, right? I can do, maybe this is the next example, but here, so in this curve, say I put my P0 on the component corresponding to these edges, then my divisor will be P1 plus P2 plus P2. And then I have two ways of putting these 2 points. So I could put both of them here or one and one. And K varies with this. Exactly. So this is what this slide is saying in genus 3. So in genus 3, the degeneration is to the union of two conics. So x is given by x0, x1. I fix a point on x0. And my divisor here is P1 plus P2 plus P3. And again, K is the degree of the divisor restricted to x0. And then now I can put my 3 points in this way. So I could put 1 point on x0, 2 points on x0, or 3 points on x0. And for these 3 different pictures, so okay, so the I have 3 different Delaunay sets that can appear in this case, which are hypersimplex 1, 4, hypersimplex 2, 4, hypersimplex 3, 4. And these are the uniform matroid of, and these Grassmannian, they have the same matroid of these polytope. And this would be like basically the Grassmannian second construct, for instance, with this method. And so basically what happens, like the intuition is that these different K-n solitons are parameterized by the different Voronoi vertices. So here we deal with these non-special divisors. So it's just, I don't allow multiplicities. I actually want G honest distinct points. And we notice that the combinatorics of the Voronoi and the Delaunay subdivision correspond to this possibilities. So one other connection that we noticed was with these strongly connected orientations of the graph. And so okay, what is a strongly connected orientation? Let me say this first. This is an orientation for which there exists an oriented path between any two vertices. And these strongly connected orientations, they appeared in works by Caporaso Viviani, or in particular, in this work by Amini, there is a more general version of the theorem I'm not talking about now. And this is that the vertices of the Voronoi polytope associated to the banana graph is in bijection with this strongly connected orientation. And so this goes back to the picture I said before. So I said this thing with the signatures, and these are in fact signatures I can give to the edges. So that's why working in the space of edges make this clear. And so this is these strongly connected orientations here. This is the Voronoi polytope in genus 3. There are these three. So in fact, there were these three families of Delaunay polytope. So the ones I had in mind here. Again, at delta 1, 2, delta 2, 4, and delta 3, 4. And then each of them has a strongly connected orientation associated to them. So we arrived to these by different means, and then we realized this is more like in a mini result, it's for any graph. And so it's actually between the poset of strongly connected orientations and the poset of the faces of the Voronoi polytope. And so basically these orientations, they also make sense for Grassmannians and the combinatorial objects associated to Grassmannians. So there's something called Flevi graph corresponding to these sets, and these orientations are those that make sense also in this set. And this is so the oriented matroid associated with the graph and the orientation agrees with the matroid we can associate it. I think I didn't say how. Maybe I skip this because there's a few things I should have said during the things that. But basically, that so there is a matroid story one can associate to this oriented graph, and these matroids will make sense with the matroid that we care for the KP story. So a few things we plan to work on in the future. So there's this problem of reality and regularity. So in this picture, basically there is. So to get a real regular soliton, not every normal, so we're fixing a point on a distinguished component of the curve. And then one takes a normalization of the curve with respect to that component, and not all normalization will lead to a real regular soliton. And this can be formalized in a combinatorial sort of description where non-crossing are. So this doesn't matter if you're complex, these numbers will not be ordered. but in the normalization, this would be. So these are the sort of pictures that Simonetta will draw in her papers, and they represent a normalization of this. So one more family one can look at is just adding loops. What happens to the two solitons and first, this should not be too hard to formalize. There is a tropical theta function, so there should be an analogous version of what we're doing here, where the Riemann theta function is obtained by like actual max-min algebra, so two people that know that, and this was worked out by MaPhyAG, for instance. And so, yeah, that's one thing that we should look closer. And of course, so what we're doing now is try to generalize this to all families of graphs. Thank you, Sophia.
Thank you for the wonderful talk. Any questions? I have a question, but it's a wish more than a question. I mean, you mentioned some relation with the polytopes and the generalized Jacobian. I don't know if you can give us a glimpse, or it is like asking you to explain a whole paper. I don't know. I mean, is it possible to give some glimpse, or maybe not? I don't know.
Yes. So in these, wait, let me think what's a good strategy. But so basically, well, okay, it's a bit in here that this theta function represents the tropical theta divisor, and I think people have mostly looked at the Voronoi. So the tropical theta divisor in MaPhyAG is supported on the Voronoi.
Okay.
And then there is this dual subdivision. So in MaPhyAG work, this is this would be so he mentioned these are these two, the tropical theta divisor and that on the Delaunay's polytope are related by a Laplace transformation. And also in all of these works by Caporaso and Viviani, I think people mostly work on the Voronoi subdivision. And then for us, it was from this degeneration sort of natural to work on the Delaunay. And so this might be like a different compartification of Jacobians that could be explored more. This is a bit speculation, but this is a bit the sense we have. So there's also work by Alexeev, Valery Alexeev on this, where maybe there the Delaunay is also mentioned. So there might be like also on the Delaunay set some sort of compartified Jacobians.
Thank you. Also another question would be, what does it mean Torelli theorem in these cases? Because the Torelli theorem is covering the curve, but here, what is? Because this is the Caporaso.
So here on the AG, so sorry, on the N, so instead of MG, there would be MG bar, where the generations are represented by metric graphs. So these stable degenerations are these trivalent metric graphs. And then on the AG bar, there are these tropical Riemann matrices. And I think in general, so if you define it this way, that to every graph you assign this matrix, the map is not injective on the but I think you need to mod out by contraction of bridges. So for instance, I had this example of the dipole with the edge that will lead to the same So that's
Okay, I understand.
yeah, I think we have lots to understand in this picture. I think it would be very helpful to us to know all of these also better. And then I guess the fact that like we're working with this motivation of KP gives a different sort of like lens on the on this picture.
More questions? So then, thanks again.
Thank you.